Black holes are often described as cosmic vacuum cleaners, objects that swallow everything around them and destroy whatever falls inside. This image is dramatic, intuitive, and deeply misleading. Black holes are not holes in space, and they are not regions where physics breaks down completely. They are precise solutions of modern physics, governed by clear rules, measurable effects, and predictable behavior. To understand what black holes really are, we need to move away from familiar images and focus on what physics actually says. A black hole forms when a large amount of mass is compressed into a very small region. The result is not a tear in reality, but an extreme curvature of space-time. Gravity becomes so strong that space-time itself bends inward in a way that leaves no path back out. This is the key idea. A black hole is not defined by what it contains, but by how space-time behaves around it. The defining feature of a black hole is the event horizon. The event horizon is not a physical surface. It is a boundary in space-time. Once an object crosses this boundary, all possible future paths lead deeper inward. Escape is no longer an option, not because of a pulling force, but because space-time itself is shaped that way. From the outside, a black hole can be described using only a few quantities: mass, spin, and electric charge. Everything else about the matter that formed the black hole becomes inaccessible to the outside universe. This simplicity is not a limitation of our measurements, it is a fundamental feature of black holes. What happens as something approaches a black hole? Far from the black hole, gravity behaves much like it does around any other massive object. If the Sun were replaced by a black hole of the same mass, Earth's orbit would remain almost unchanged. The dramatic effects only appear close to the event horizon, where space-time curvature becomes extreme. As an object falls toward a black hole, time behaves in a surprising way. To a distant observer, the falling object appears to slow down. Its clock ticks more and more slowly as it approaches the event horizon. Light emitted from the object becomes increasingly redshifted and dimmer until it fades away. From the outside, the object never quite seems to cross the horizon. But this is only one perspective. From the point of view of the falling object, nothing special happens at the event horizon, at least not for very large black holes. The object crosses the boundary in a finite amount of time, without encountering an infinite force or a physical wall. The laws of physics do not suddenly stop working at the horizon. This difference in perspectives is not a contradiction. It is a consequence of how time and space-time behave in strong gravitational fields. Different observers experience time differently, and black holes make this difference impossible to ignore. Inside the event horizon, the structure of space-time changes dramatically. What used to be a direction in space becomes a direction in time. Moving inward is no longer a choice. It is as inevitable as moving forward in time. Just as you cannot stop time from advancing, you cannot stop the inward progression once the horizon is crossed. At the center of a classical black hole lies what physics calls a singularity. This is not a point in space like any other. It is a region where space-time curvature becomes extreme, and our current theories lose their predictive power. The singularity is not necessarily a physical object. It is a sign that our description is incomplete. Do black holes destroy information? For a long time, physicists believed that anything falling into a black hole was lost forever. This idea led to a deep conflict between gravity and quantum physics. Quantum theory suggests that information cannot be destroyed. Gravity, at least in its classical form, seemed to say otherwise. This tension is known as the black hole information problem. Over the past decades, evidence has accumulated that black holes do not destroy information in the fundamental sense. Instead, information may be encoded in subtle correlations at the event horizon, or carried away by radiation. Black holes are not completely black. According to quantum physics, black holes emit a faint form of radiation, now known as Hawking radiation. This radiation is incredibly weak for astrophysical black holes, but it has profound implications. It suggests that black holes can slowly lose mass and, over extremely long timescales, evaporate. This means black holes are not eternal prisons. They are physical systems that evolve, interact with their surroundings, and obey deeper laws that connect gravity, quantum mechanics, and thermodynamics. Why do black holes matter? Black holes are not exotic exceptions. They are natural consequences of gravity. Almost every large galaxy appears to host a supermassive black hole at its center. These black holes influence how galaxies form, how stars move, and how matter behaves on the largest scales. Black holes also serve as laboratories for extreme physics. They push our theories to their limits and reveal where our understanding breaks down. By studying black holes, we learn not only about gravity, but about the fundamental structure of reality itself. Black holes are not cosmic monsters. They are precise, predictable, and deeply informative. They show us what happens when gravity becomes geometry at its most extreme. Black holes are not what you think, and that changes everything. Next, we'll look at what happens to time near a black hole, and why it nearly comes to a stop.
If this helped, hit like and subscribe for one 10-minute idea every day.